In this lecture, we'll learn about two new functional groups, the alkene functional group and the alkyne functional group. Alkenes and alkynes are both examples of hydrocarbon compounds. We learned quite a bit about hydrocarbons in our last unit. That unit focused on alkanes, which are hydrocarbons that have all single bonds. Alkenes, on the other hand, are hydrocarbons that contain one or more carbon-carbon double bonds. It's important to realize that alkenes will also contain carbon-carbon single bonds, but once a hydrocarbon contains at least one double bond, we classify the entire molecule as an alkene. Likewise, alkynes are hydrocarbons that contain one or more carbon-carbon triple bonds. There are molecules out there that contain both double and triple bonds between carbons. To keep things simple, we won't focus on them specifically in this class, but you should feel confident that what we learn about simpler alkenes and alkynes will also hold true for those more complex molecules. When we compare alkanes, alkenes, and alkynes, we find some similarities and some differences. Physically, these molecules tend to be very similar to each other, so they tend to share the same trends in melting point and boiling point. They tend to be colorless and odorless. Chemically, however, alkenes and alkynes are far more reactive than alkanes. We've learned previously that alkanes don't undergo that many types of reactions. Alkenes and alkynes, however, can undergo many types of reactions. One way that alkanes, alkenes, and alkynes differ from each other is in terms of the amount of hydrogen atoms that each type of molecule can contain. Alkanes, because they have only single bonds, have tetrahedral carbon, meaning that each carbon will always have 4 bonds attached to it. Let's look at an example in the molecule ethane. Ethane has 2 carbons, and therefore we know that it must have 6 hydrogen around it so that each carbon has 4 bonds. Because there's no way to attach more hydrogen to 2 carbon, we say that this molecule is saturated. All alkanes are classified as saturated molecules. Let's contrast that with an alkene. If I take 2 carbons and I double bond them together, the molecule that results will only have 4 hydrogen. The fact that a double bonded carbon only has 3 bonds touching it means it doesn't have the maximum number of hydrogen atoms possible. As a result, we classify it as being unsaturated. Both alkenes and alkynes are classified as unsaturated molecules. 2 or more of the carbons in the molecule have less than 4 bonds, thus limiting the amount of hydrogen atoms that can be present in that type of molecule. Especially with alkenes, we often run into the terms monounsaturated versus polyunsaturated. As you can guess, a monounsaturated alkene contains just 1 double bond. A polyunsaturated alkene can contain 2, 3, or more double bonds. Finally, notice that this change from single bonds and saturated molecules to a double bond and an unsaturated molecule will have an effect on the molecule's geometry. We know that the carbons in an alkane are tetrahedral. The carbons in an alkene are trigonal planar, also known as planar triangular. These are essentially a flat type of molecule, rather than that 3-dimensional tripod we've become used to looking at with tetrahedral geometry. So alkenes have trigonal planar geometry. The bond angle in trigonal planar geometry is 120 degrees. We'll see that this affects how we draw the molecules in some circumstances. Let's talk about how to name alkenes and alkynes using IUPAC nomenclature. Because we've already learned how to use the IUPAC naming for alkanes, most of what we learn in this section will seem very familiar. We saw that alkanes have the prefix ane, and hence the fact that many of our names ended in words like methane, ethane, propane, and so on. For the alkene and alkyne functional groups, we'll use different suffixes. Not surprisingly, the alkene functional group uses the suffix ene, and the alkyne functional group uses the suffix yne. So let me give you an example of one of these molecules and see if you can name it. Even without going over the rules for IUPAC naming, you probably noticed two things right away about this molecule. First of all, there's a double bond present between two of the carbons, so this is an alkene. Second, you probably noticed that there's 6 carbon atoms. We already know that the prefix that we use when 6 carbon atoms are present is hex. So when we put this together, we get hexene. That is part of the correct name, but if we say hexene, we actually don't distinguish this molecule from several others. And here's the reason why. In this molecule, the double bond exists between the carbon that's second to the left and the carbon that's third to the left. If we call this molecule hexene, then how will we differentiate between a 6-carbon alkene that has the double bond in any other position, perhaps on the first bond? Remember that IUPAC nomenclature has to give completely unique names to every individual molecule, so we do need a few more details to name this molecule correctly. When using IUPAC nomenclature, again, the rules are going to seem very similar. So just like with alkanes, we'll start by numbering the carbons in the chain. Again, we have the choice of whether to number from the left side or the right side. And again, we're going to choose so that we get the lowest number possible. In this case, we're now dealing with a double bond. We want to get the double bond to the lowest number possible, whereas previously we were dealing with branches, and we had to choose numbering to get the branch at the lowest position possible. So I have two choices. One is to number from the left, 1, 2, 3, 4, 5, 6. The other is to number from the right, 1, 2, 3, 4, 5, 6. Notice that the top options, or numbering from the left, give me a lower position for the double bond. The double bond is located between the second and the third carbon, and by IUPAC rules, we always use the number that indicates where the double bond starts. So in this case, we'll simply designate carbon number 2. That's going to indicate that the double bond is between the second and the third carbon. When it comes to actually putting together the name, you actually have two possible options. One option is what I prefer, and it's what you'll tend to see the most of in the real world. The other option is what your book uses. Either one is going to be worth full credit in this class. The version that your book will use will put the number designating the location of the double bond in front of the name of the molecule. So it would call this 2 dash hex for the fact that there's 6 carbons and ene for the fact that it has a double bond. You would pronounce it 2-hexene. As before, remember that we separate letters and numbers with a dash. That's what your book will put as the correct answer, and most scientists would be fine with that. It does get more complicated, however, when we start to have multiple double bonds and much more complex molecules. What I don't like about this is the fact that the 2 is very far from the information that I'm dealing with a double bond. So here's what the most current IUPAC recommendation for naming is. We would actually call this hex and then put the 2 before the suffix ene. The downside to this name is that it's a little bit harder to say, hex 2-ene. The upside is that there's no room for confusion here. It's obvious that we're dealing with a double bond on the second carbon. And remember, it's implied that the double bond starts on the second carbon and then what goes to the next one in line, the third carbon in this case. Let's do some practice. Name this molecule. Again, we have to choose whether to name this molecule by numbering from the left or numbering from the right. Numbering from the right gives us the lowest possible number. So here's 1 carbon, 2 carbons, 3 carbons, 4, 5, 6, and 7 carbons. I can see that the double bond starts on the third carbon. and it's my choice how to actually write out the name. One option is to call this 3-heptene, the hept indicating that there are 7 carbons and the 3 indicating where the double bond starts. The other option, which is also good for full credit, is hept-3-ene. Let's try one more. Here's an example of an alkyne. Go ahead and name this molecule. To get the correct name for this molecule, I would choose to number from the left side. And I notice that again I'm dealing with 7 carbons. The triple bond starts on the 2nd carbon. So when I name this, it'll be similar to what I did above, but now I'm dealing with a different suffix. So the 2 correct ways to name this would be to call this 2-heptyne, or we could also call this hept-2-ine. One thing to watch out for when naming these molecules: no matter what it looks like on paper, make sure that your backbone contains the double or triple bond. And that means sometimes you'll have to choose a backbone that might be shorter than you think. Of course, we always have the goal of choosing the longest backbone possible, but we never want to see our double or triple bond end up on part of a branch. That would enormously complicate our naming. So just make sure when you're highlighting the backbone, circling it, or doing whatever you've decided is the most comfortable way for you to name things, make sure that it includes any double or triple bonds in the molecule. Many molecules contain more than one double or triple bond. When that's the case, we have a shortcut that allows us to efficiently name the molecule. Because it's much more common for us to run into this with double bonds rather than triple bonds, I'll focus on those here, but I assure you the rules are the same for triple bonds. We use the same prefixes that we used when we had multiple branches of the same type. Prefixes like di, tri, and tetra. And where we put them is right before the suffix. Consequently, if you have 2 double bonds in a molecule, we would say that rather than it just being an ene as a suffix, we would say diene. If we had 3 double bonds in a molecule, we'd call it a triene. If we had 4, it would be a tetraene, and so on. So for example, a molecule like this, which has double bonds on both the 2nd and the 4th carbon, could be named in 2 different ways. One would be to name it 2,4-hexadiene. The other would be to split the name. We'd call it hexa 2,4-diene. Either one of these would be correct. It's very rare to run into triple bonds on cyclic structures, but double bonds on a cyclic structure, or a cycloalkene, are very, very common. Naming cycloalkenes is basically a combination of the rules we learned for alkene naming and the rules we learned for cycloalkane naming. For instance, let's name this molecule. Pretty much the only thing I need to tell you to make sure you do it correctly is that by definition, we have to make sure that we number the carbon so that the double bond is located between carbon 1 and 2. Having said that, you can go clockwise or counterclockwise to get the lowest number for any other branching substituents possible. Take a second and name this structure. I have 2 options for naming the structure. One would be to number clockwise and say that the double bond starts on carbon 1, proceeds to 2, 3, 4, and 5. I would have a total of 6 carbons in this ring. The other option is to start here and number 1, 2, 3, 4, 5, and 6. Notice that the second option, or the numbers written on the outside of the ring, puts my branch at carbon number 4. Both of these, however, were done correctly because I stepped from carbon 1 to carbon 2 directly over the double bond. Notice that I can't just start on one carbon that's touching the double bond and go in the other direction. Because we want to get the lowest numbers possible, the correct option for this name is to number it according to the numbers that are on the outside of the ring. The name of this molecule would be 4-methyl, because I have a methyl substituent, cyclohexene. 4-methyl cyclohexene. I don't have to number the position of the double bond because by definition it's between the first and the second carbon. If you're dealing with a more complex molecule where you have multiple double bonds on a cyclic structure, then it's customary to number. So for instance, if I were to add another double bond to this structure, then I would want to specify both where the first double bond and where the second double bond exists. You'll see more examples of that in your practice problems. Now we come to a brand new topic because it's a topic that didn't affect alkanes but will affect the alkene functional group. It won't affect alkynes, so we won't be discussing them during this part. Geometric isomers are related to two topics we have covered, however, because they have to do with how a molecule is arranged. We've already seen that all molecules can have multiple conformers, meaning you can bend and twist most organic molecules into multiple positions. It doesn't actually change the molecule, but it just shows it in different conformations. On the other hand, you can have structural or constitutional isomers of many organic molecules. Remember that structural isomers are molecules that have the same chemical formula, but their structures are otherwise different. In other words, their atoms are connected in different ways. Geometric isomers are somewhere between the two of these, and the reason for that is this. We said that in alkanes there's many different possible conformers because carbon-carbon bonds can rotate. But when we start dealing with alkenes, we're dealing with carbon-carbon double bonds, and carbon-carbon double bonds cannot rotate at all. This means that when you have a shape or a conformation to a molecule and you put double bonds on that molecule, it's almost like it locks it in place. As a result, we get geometric isomers. Geometric isomers are molecules that have the same chemical formula and the same structure, but they're arranged differently in space. Here's a classic example. This is the molecule 2-pentene, or pent-2-ene. What I'd like you to do is draw the structure of this molecule, and you can draw it in any form you want, but you have to draw it around what I'm writing now, the carbon-carbon double bond. Fill in the empty spaces on the end of those bonds to completely draw this molecule. Pause the video while you do it. There are two different ways you could draw this molecule. Notice that the carbon-carbon double bond is between the second and third carbon. So one way to draw this structure out would be to write CH3, which is the first carbon in the molecule, and then I've already got the carbons from the double bond, so then I would have to add in CH2 and CH3. If you draw this out in more detail, or if you condense it into a line structure, that's fine too. That means that these other bonds would have hydrogen on them. That's one possibility. And in fact, if you had moved this one carbon group down here, or this 2 carbon group up there, that's really the same. Here's another possibility that you may have drawn. If we start the same way by having the CH3 group on the top of the double bond, what about if I write the 2 carbon group on the top of the double bond, or on the same side as that first group? By doing that, I've created what's called a geometric isomer. These molecules have the same chemical formulas and the same structure because all the same carbons are connected to each other, but they are significantly different. The molecule on the left side is what's called the trans isomer, and trans means across. So the meaning here is that across the double bond, we see one of my carbons going to the other carbon. The other type of molecule I have is what's called a cis molecule. Cis should make you think of same side, like sisters are on the same side of the family. The cis molecule has those carbon groups on the same side of the double bond. These molecules can have dramatically different properties despite the fact that they have the same chemical formula and the same structure. They're what we call geometric isomers. Let's try an example. Draw the structure of trans-4-methyl-pent-2-ene. As you do this, be sure to check your structure to ensure that it does show trans geometry. You'll notice that if you condense your structure too much, it might not be cis or trans. Give it a try. Let's try some practice. Draw the structure of trans-4-methyl-pent-2-ene. I recommend starting with a relatively expanded structure rather than doing too much condensing of your different carbon and hydrogens. I also recommend avoiding the line structure for a couple more minutes until we talk about it specifically. Okay, so to draw the structure of trans-4-methyl-pent-2-ene, there's quite a few correct options. As I mentioned, you want to avoid condensing your structure too much, and I want to start by showing you why that's a problem. If I draw a condensed version of this structure, I might end up with something like this. My first carbon is connected to my second carbon, which has a double bond. Then I move on to the third carbon. My fourth carbon has a methyl group attached to it, and I complete the molecule by writing the fifth carbon. This is the structure of 4-methyl-pent-2-ene, the correct molecule, but it's not trans 4-methyl-pent-2-ene, and it's also not cis 4-methyl-pent-2-ene. The reason is, in that condensed form, there's no way to tell whether your carbon chain went on opposite sides of the double bond or on the same side. This is one of the reasons it's important to expand the area at least around the double bond. The most common way you'll see this drawn is the same way we drew the previous example. Because the molecule's name is based on the double bond geometry, I'll draw the double bond first, and then I'll connect the required carbons and hydrogens to complete the structure. Because this is a trans structure, I need to make sure that I connect the carbons on opposite sides of the double bond, so one points up while the other points down. The remaining structure includes the methyl group as well as the hydrogens and other carbon I need to complete the chain. This is the trans version of the molecule. It's also the most common way you'll see it drawn. Again, if you move this particular carbon to that hydrogen, that's still correct as long as this entire group also moved to up there. What do you think this would look like as a line structure? Well, take a second and draw it. Generally, trans geometry around a double bond is much easier to show in a line structure than cis geometry. Here's why. If I were to draw out a 5-carbon chain according to this molecule, it would look like this. Here's my first carbon, second, third, fourth, and fifth. The double bond was between the second and third carbon, and I also had a methyl group on the fourth carbon. This is what trans 4-methyl-pent-2-ene looks like when drawn as a line structure. Let's take a second though and compare this to what the cis version of the molecule would look like. One easy way to draw the cis form of a molecule, if you already have the trans form written out, is simply to keep one half of the molecule the same and switch what's on the other side. In this case, that means my hydrogen will point down and my other carbon group will be pointing up. This is the cis form of this particular molecule. To draw this as a line structure, I can no longer use a perfect zigzag. In this case, my first carbon and second carbon are a single bond. My third carbon is a double bond. The single bond to the fourth carbon, however, has to be on the same side. So if I start it in the same manner as what I did for the first line structure, there's my first single bond. Here's my first double bond. But now, in order to make sure that these single bonds are facing in the same direction, I can't move up. In other words, I can't continue the zigzag pattern. I'd actually have to point this other line down. It still works by the definition of a line structure, but the result is that it creates a little bit of a plateau, or if we had drawn this in reverse, it would look like a little bit of a valley. To finish the molecule, I still need to add 2 more carbons, but notice that it looks quite a bit more awkward than what we drew above. This is one reason it's very easy to identify cis and trans structures when you see a line structure. If the zigzag continues as you move past the double bond, you're looking at the trans version of a molecule. But if you see what's generally referred to as a valley or a plateau, then we're looking at the cis version of the molecule. Both are completely legitimate ways to draw the structure, but you'll have obvious preferences as you're drawing them out yourself. In most cases, choose whichever version is easiest for you to draw, whether it's an expanded structure, a semi-condensed one, or a line drawing. One of the places that people have usually heard the terms cis and trans before is when it comes to fats, and they actually make a very good example of seeing these molecules in real-life use. Fats in general are actually a really interesting topic throughout organic chemistry, and for that reason we'll learn about them at several different points this quarter. For today, I just want to show you a couple topics that do involve fats that come directly out of this particular unit. This is an example of a fat, or what a chemist would actually call a fatty acid. We call it a fatty acid because all fats contain the functional group carboxylic acids. The carboxylic acid functional group, which you see here at the right end of the molecule, is something we'll study in depth later this quarter. What I want to focus on now is just the fat part of the fatty acid, which is the carbon chain. This particular fatty acid is what's called lauric acid. Lauric acid is found in many different foods. One of the ones it's most famous for is coconut oil. That's a little bit of a misnomer because coconut oil is actually more of a whitish sludge. You can actually buy it at the store. It smells great and it's great for cooking. But it's not terribly healthy for you, and here's why. If you look at the carbon chain on this fatty acid, you'll notice that we would classify it as being saturated. There's no double or triple bonds present. As a result, lauric acid is an example of a saturated fat. When we say the term saturated fat, we're actually saying that we have the molecule of a fatty acid and it's got all of its hydrogen possible. It's saturated. An interesting consequence of the fact that it's saturated is that all those hydrogen atoms inhibit movement, and as a result, saturated fats tend to be solid at room temperature. So when you think about substances that have a lot of fat that are solid, ones that come to mind to me are coconut oil, butter, Crisco, and other shortenings. Those tend to be saturated fatty acids. One distinction here, the fat that's actually in the human body is a type of fatty acid that's actually reacted to form a more complex molecule called a triglyceride. If you go on to 123, you'll cover that in a lot of detail. But back to our fatty acids. As you probably already know, saturated fats are generally considered to be unhealthy. What that means is that if you consume a lot of saturated fat, it can have a detrimental effect to the human body. It affects things like your cardiovascular health. Let's look at some other types of fats. This molecule is called oleic acid. Oleic acid makes up about 50% of the weight of oils like canola oil, and these are generally considered to be more healthy than saturated fats. What do you notice right away that's structurally different between oleic acid and lauric acid? Well, you should notice that there's a double bond in oleic acid. The double bond means that this is an unsaturated fat, and something as simple as that small double bond in that large structure actually gives it enough flexibility that these tend to be liquid at room temperature. In other words, these are what we use as cooking oils. Oil fats tend to be unsaturated, where solid fats tend to be saturated. And these in turn are considered to be healthy. Now, healthy is a relative term here. They're healthier than saturated fats, but of course everything in moderation is the healthiest thing for the human body. So if you consume a large amount of these fats, they can also become problematic just because they have a lot of calories. This might be disappointing news to some of you. Don't blame me, but if you flip over the label on your oils, you might be surprised how many calories are in 1 tablespoon of canola oil. One more type of fat to consider. Before we look at it, look again at this structure of oleic acid. Notice what the line structure of oleic acid looks like around the double bond. Does this molecule have cis geometry on its double bond, or does it have trans geometry? Well, when you look carefully at the geometry around that double bond, you can see that it forms a plateau. Even more significantly, it means that the carbon on the left side and the carbon on the right side both leave the double bond pointing in the same direction. That means that this bond has cis geometry, and as a result, this unsaturated fat is a cis unsaturated fat. It's what most unsaturated fats are. So what happens when we take that cis geometry in oleic acid and we change it to trans geometry? Then we're looking at a trans version of the oleic acid molecule. It actually has a totally different common name, which we don't usually hear. But notice on the line structure, now we have that nice regular repeating zigzag pattern. And while that looks good on paper, the downside is now we're also looking at a trans fat. And trans fats, as you probably already know, are now considered by most scientists to be the most unhealthy type of fat for humans to consume. Again, it's all relative. If you're drinking gallons of unsaturated fat a day, that's a lot more unhealthy than consuming very, very small amounts of trans fat. But when we compare saturated, unsaturated, and trans fats, which are really trans unsaturated fats, trans fats tend to have the most detrimental effects on the human body, at least in ways we can measure. So why have we only started to hear about trans fats in the last 5 or 10 years? Well, the answer really comes from the fact that trans fats don't exist in large amounts in nature, but they have started to exist in large amounts in our modern food supply. And the reason is because they're actually a byproduct of the process that takes an unsaturated fat, like oleic acid, and changes it into a saturated fat. Why would someone want to take an unsaturated fat, something that's considered to be healthy, and change it into a saturated one? Well, the answer goes back to something we brushed on earlier. Saturated fats are alkanes, or at least have alkane-like properties, and therefore they're a lot less chemically reactive than unsaturated fats that contain alkenes. So really what's happened in our modern world is we've taken unsaturated fats in food that might be very, very susceptible to things like oxidation or other chemical reactions that impact shelf life, and we learned that there's a process we can do, which we'll look at later in this section, called hydrogenation. When you hydrogenate an unsaturated fat, you add hydrogen to it, breaking bonds to create a saturated fat. While it gives you a less healthy product, that product is now a lot more stable, and sometimes people think it'll taste a lot better too. The downside is when you start to break those double bonds, you get some that reform in the trans geometry. The consequence of this is that our modern production processes that produce foods with saturated fats also produce foods with trans fat. And here's a nasty little thing to watch out for when it comes to reading food labels. All that a food producer has to report when they write their food label is the amount of trans fat that they measure. But anytime you're reading a food label and you see that it's a hydrogenated food, it might contain something like partially hydrogenated soybean oil, that means they took the unsaturated soybean oil and they hydrogenated it. And in that process, it creates more trans fats. So don't believe a food label that says there's no trans fat present if the same food label also includes partially hydrogenated anything. It's a natural byproduct, so it's naturally going to be present even if it's in very small amounts. Before we finish up this lecture, I just want to give you a preview on where we'll go next. In our next lecture, we'll start to look for the first time at alkene reactions. And really, it'll mark the entry into the world of organic reactions in general, because we only looked at 2 very limited definitions of alkane reactions previously. Alkenes are very reactive molecules, and there's many types of reactions they can do. One reaction, which includes the hydrogenation reaction that results in things like trans fats, is what's called an addition reaction. Addition reactions happen whenever you have a double or a triple bond, and you break that bond in order to add new atoms to the molecule. You can also reverse that process. We'll see that you can do what's called an elimination reaction. An elimination reaction happens when you remove atoms and you use the electrons that were used in the bond to those atoms to create double or triple bonds. We'll also talk about substitution reactions. Substitution reactions, just like the name implies, are reactions where you remove one atom and you replace it with another atom. There's also a type of reaction called a rearrangement reaction. Because they're a little more technical in nature, we won't touch on those in this class. So that's where we'll pick up in our next lecture. Remember to work your practice problems on everything covered in this lecture, and let me know if you have any questions.